Okay, now that we've spent several days talking about different properties involving logarithms, we're going to move into seeing how logarithms are actually used and applied in different areas. And so a lot of these problems are going to move into some application problems so that we can kind of see how they're useful here. Okay, the main purpose actually of a logarithm is to help us solve equations, oftentimes when our variable is in the exponent. But we're going to revisit something that we talked about right at the very beginning with logarithms. We talked about these things called common logarithms, and a common logarithm is a logarithm whose base is 10. Okay, that is typically that log button that you see log along the left side of your calculator. That button can only be used if the base of your log is 10. Now, the way this actually works, I know when you press that button, it doesn't show you the little subscript 10. You actually don't see any number there for the base at all. Similar to when you type in the square root button, it doesn't show you that there's a 2 down there for your root, but we know that it's implied. So what you're often going to see when you're dealing with a common logarithm is you're just going to see log, and it's going to look like there is no base. If you see no base, assume that you're dealing with a common logarithm and the base is 10. So these four problems that you see here, they are as easy as they sound, or look, I should say. They're wanting us to round these answers to the nearest 10,000th, which means carrying it out to 4 decimal places. And you can see on none of these logarithms are they showing us a base. And so the assumption here is the base on all 4 of these is a 10. So you would just be using that log black log button along the left side of your calculator, and you would just be typing these in exactly as you see it. So if you type log 5 on your calculator and then round to 4 places, you're going to see 0.6990. If you type log 0.3, this would be the number that you would see, and we're not going to type all those in because that's just very simple. You're just typing it in, essentially rounding it to 4 places. Okay, let's take a look at some of these word problems here. Okay, this first word problem is talking about how loud something is. Typically, when we talk about how loud something is, it's generally measured in units called decibels. And so you can see here with most of these problems, they're going to be giving you some type of equation. As you read through the problem, you want to make sure that you're making note what the variables in the equation are representing. Okay, so it's telling us here that the capital L is the loudness of some object, and it's going to be measured in decibels. They go on and say the I, the capital I you're seeing there, is the intensity, okay, the intensity of that particular object. And I don't think that it tells us what the intensity is measured in. And so anytime they don't give you a unit of measurement for a variable, we're just going to go generic and just say units if they don't give us what that measurement is. So it says here, residents that are living several miles from a concert venue can hear the music at a loudness of 66.6 decibels. So I want you to make note here, they're giving us the loudness. The question is, what is the intensity of the sound? So they're asking us to find I, and they're giving us L. Okay, so we're going to take the equation that they gave us up here. We're going to plug 66.6 on the left side for the loudness, and then we're going to take a look at this equation and see if we can tackle solving this for the variable I. Okay, now let's think through some of the properties that we've been learning here the last several days. We have learned that if we're dealing with an equation, we really want to tackle solving the equation by thinking through that property called the one-to-one property. Remember, you want to be able to have one logarithm on one side. Make sure you have one logarithm on the other side. Now, I see a logarithm on the right side. Currently, the left side is just the number 66.6. If I want to change 66.6, though, into a logarithm, I should be choosing the same base as the log that I'm seeing over here on the right side. If I'm using that as a 10, I also have to put a 10 here so that these are the same. And then the number 66.6, I'm going to move that up into the exponent there. Okay, that would be how 66.6 would look as a logarithm. Okay, I'm going to keep the right side the same. And now I think I can apply the 1-to-1 property. I'm going to cross off the log and the base 10 from each side. That leaves me with 10 to the 66.6 power is what I represents. Okay, now you have two options. You can leave the answer like that and just say the intensity is 10 to the 66.6, and I'm just going to call this units since they didn't give us a unit of measurement. Or if you type that in, you can write out what that number is. It's probably a really big number in scientific notation, but you could write that number out and that would be fine as well. Okay. All right. So I'm just going to leave it like that. All right, let's take a look at example 3. Now, again, let's note the equation and let's note what our variables are representing. It makes it easier to tackle, okay? The amount of energy, E, okay, so amount of energy, E, it's measured in a unit called ergs, that an earthquake releases is related to its Richter scale magnitude, M. So Richter scale is magnitude M. So I'm going to just kind of color code these here so that we can see what we're dealing with. Okay, it says use the equation to find the amount of energy released by the 2004 Sumatran earthquake, which measured 9.0 on the Richter scale and led to a tsunami. So what are they asking us to find? They're asking us to find the amount of energy that's released. So we are trying to, in this problem, find the capital E variable, and they're giving us the magnitude on the Richter scale. They're giving us the 9.0. Okay, so we're going to solve for the E, and we're going to substitute 9 in for the magnitude M. Okay, so you can see that would be our substitution here. Okay, well, it's looking like everything on the right side here is just constants. So let's go ahead first of all and just add all those numbers up together. We can combine them together on our calculator. If we type that right side into the calculator, I believe you get 25.3. Okay, well, I already see one logarithm on the left side of the equation. Now remember, we said up above, if you don't see a base, the assumption is that's a common logarithm and the base is 10. I'm going to just draw it in so we can see it nice and clear. Okay, however, on the right side, we do not have a logarithm there, so I'm going to need to turn the number 25.3 into a logarithm by writing it as log base 10 of 10 to the 25.3 power. Okay, I like to draw the bases in because when you're doing the 1-to-1 property, you want to make sure that what you're crossing off is the log and the subscript base. Okay, that's going to leave behind the E, which is the amount of energy in ergs, equals 10 to the 25.3. Okay, so you can leave it like that if you like and label that ergs, or if you want to type into your calculator 10 to the 25.3, again, it's going to be a really big number. Okay, I'm just going to kind of carry that out. I'm going to write it in scientific notation because it's so big. When you see that E, if you're looking at your screen and you type that in, see that capital E at the end? That's the scientific notation. You could write the answer either one of those two ways there. Okay. All right, let's take a look at one other word problem before we are introduced to something called the change of base formula. This word problem, number 4, is a mountain problem. It's trying to figure out what the air pressure is at the top of various mountains that are different heights. This particular problem is very, very important. You're going to see problems like this pop up on the next several worksheets, and it's very likely that a problem like this is going to pop up on a test. Okay, so please take really good notes on this example and use these notes to help you as you're trying to do problems similar to this on your homework. Okay, so if you guys have ever flown in an airplane, you probably noticed that as you're ascending or descending, your ears tend to pop, and that's all related to the fact that the air pressure is changing, particularly at different altitudes, at different heights here. So let's look at what our equation is, and we're going to look at what our variables are here. It says the atmospheric air pressure P, measured in pounds per square inch. So that's what the P is, the air pressure. And the altitude, A, in feet, because that's how high you would be, are related by the logarithmic equation given below. How many times greater is the air pressure at the top of Mount Whitney, which is 14,495 feet high, compared to the air pressure at the top of Mount Everest, which is 29,028 feet high? These problems are essentially two problems in one, okay? So you're going to want to create a space on your paper where you essentially have two columns. You're going to label one column Mount Whitney, and the other column you're going to label Mount Everest. Okay. The steps on this are very important. Please make sure you're writing down everything that I am writing down here. I know this is going to feel a little bit tedious and a little bit repetitive because you're going to be doing essentially the same thing for both of these columns. Okay, now look at what the information is they're giving us. They are giving us the altitude at Mount Whitney and the altitude at Mount Everest, which is what the A is in the formula. So what we're after is we want to substitute that altitude into the formula for the A, and we want to see if we can try to solve the equation for P, what the air pressure is at the top of Mount Whitney. While I'm here, I'm going to go ahead and go over to this column as well and go ahead and substitute the altitude for Mount Everest. That way I have both the substitutions already made in each of the formulas here. Okay, so your steps to solve both of these is going to be the same. Obviously, the answer is going to be different because we inserted a different altitude here. But here's what I'm going to encourage you to do. And this is something a little bit different than what we've typically done in the past. We've generally said if you have a number in front of your logarithm, you should do the power rule and pull that number up in the exponent of your argument. Okay, I'm going to say let's not do that on this problem. Okay, if you were to pull that up, you would be putting it as the exponent on the fraction p over 14.7. These problems are going to be a little bit easier if, as your initial step, you actually remove that 55,000 number from the right side by dividing both sides by that number, okay? All right, so we're going to divide both sides by negative 55,555.56. I'm going to kind of do both these sides here at the same time. I don't know normally that I would necessarily suggest that you do that, but just to kind of expedite this, I'm going to go ahead and sort of do the same thing here to both sides. Okay, so if you look at what we have now on the right side, we have one logarithm on the right side of the equation, and there's just a 1 in front of that logarithm. Okay, that's good because we want to do the one-to-one property. So it looks like the right side of the equation, we got that set up nicely. However, the left side of the equation, there's no logarithm, and it's kind of this big, ugly fraction, but that's okay. We have turned logarithms, or numbers rather, into logarithms here for the last several days, okay? So what we would want to do is we would want to write down log base 10 of 10, and then in the exponent, you're going to have the fraction 14,495 divided by negative 55,555.56. Okay, I know that looks really messy and kind of really ugly, but that is how you would turn that fraction into a logarithm. Okay, let's do the same thing over here on Mount Everest side. Log base 10 of 10, and then you're taking that crazy looking fraction, and that's actually going in the exponent on the 10. Okay, now we should be good to do the one-to-one property. Keep in mind, you are crossing off just the log and the base from each side. That's going to leave you 10 to the 14,495 over this negative 55,000 number equals p over 14.7. Same thing on this side. Crossing off the log and the base. Okay, so keep in mind, the goal here is to solve for p, and then we can use that to answer the actual question here. So if we want to get the p by itself, I need to get rid of that 14.7. So I'm going to multiply by 14.7. That means over here, I'm going to be multiplying that by 14.7. So I'm going to do the same thing over here. So here's where you'd want to pick your calculator up, and you're going to type in 14.7 times 10, and then you're going to enter this fraction as the exponent on the 10. Okay, now these answers, you're just going to round them to two places. Over here, you get 8.06. It said the air pressure is measured in pounds, lb, per square inch, Okay, over here, if we type this side in, the air pressure at the top of Mount Everest, 4.41 pounds per square inch. Okay, so the air gets thinner as you go up. All right, now let's look what the question was, though. The question was, how many times greater is the air pressure at the top of Mount Whitney than at the top of Mount Everest? Well, let's think about this in simpler terms here. If the air pressure at the top of Mount Whitney was 8 and the air pressure at the top of Mount Everest was 4, we would say that the air pressure at the top of Mount Whitney is 2 times greater than the air pressure at the top of Mount Everest. So if one was 8 and one was 4, how did I get 2? Well, I simply divided the bigger number by the smaller number, and that's how I got how many times that smaller number fits into the bigger number. That's exactly what you're going to do. You're going to take the larger number, 8.06, divide it by the smaller number, 4.42. Okay, type that into your calculator, round that answer to two places. Roughly, the air pressure at the top of Mount Whitney is 1.83 times greater than the air pressure at the top of Mount Everest. Okay, so once you've worked through the work for finding the air pressure at the top of each of those, you divide the bigger pressure by the smaller pressure to actually answer the question. Okay, we're going to close today with these last few examples here that are discussing this idea called the change of base formula. Okay? The change of base formula essentially lets you take problems like these two here that you're seeing, where when the base is not a 10 and you can't use that common logarithm button on your calculator, how can you possibly change the base so that it is a 10 so that you can use your calculator? Okay, because right now we wouldn't be able to actually simplify these problems here at all. Okay, so here's how the change of base formula essentially works. Okay, I'm going to demonstrate it with this example that has some numbers in it. What you would do is you would actually take your logarithm and rewrite it so that in the numerator and denominator you have log base 10 in the top and log base 10 in the bottom. Now, the original argument, okay, the 11, the original argument, stays the argument of the logarithm in the numerator. But the original base becomes the argument of the logarithm in the bottom. So I think of it like this. When you think of the base of something, like if we have a tree and I say, look at the base of the tree, your eye should be drawn to the bottom of that tree. So if we're talking about the original base number, that goes in the argument in the bottom. So just kind of, I guess, think of this, that the base goes to the bottom. Okay, we'll practice that here in example 5a. Okay, we want to rewrite it using the change of base formula. I do not want you to just type it into your calculator and write down the answer. I need you to write down on your paper what you entered into the calculator to get the answer you're writing down. So I need you to write down log base 10 in the top, log base 10 in the bottom. Okay, the original argument, 20, stays the argument of the logarithm in the numerator. But again, think base goes in the bottom. But the original base, that's the 3, that becomes the argument of the logarithm in the bottom. And now that these are both common logarithms, you could type that into your calculator, log 20 divided by log 3, round the answer to two places, 2.73. Okay, we'll try one more of these and then we'll apply this to these two problems at the bottom. Okay, I'm going to write this log base 10 in the top, log base 10 in the bottom. Original argument stays in the numerator, but the original base, the 6, becomes the argument of the logarithm in the bottom. We type that in, we get 1.16. Okay. Now, here we have some problems that don't even have logarithms in them at all. In fact, these 3 problems all look like they are written in exponential form. You'll notice, look at where the x is in all these examples. The x is trapped in the exponent. This is exactly what logarithms were designed for. They were designed to help us solve equations that have variables that are trapped in the exponent. So what we're going to end up doing is we're going to end up switching the equation out of exponential form and into logarithmic form. However, the first thing you need to make sure that you have done is that you have isolated just the term that has the variable in the exponent. Like, I'm going to jump to example C real quickly here. The term that has the variable in the exponent is the 6. That 6 right now is not isolated. There's a 7 that's sitting on that same side of the equation. So what we would need to do first, before we switch this into logarithmic form, is we need to isolate that 6 so that we just have 6 to the 2x plus 1 on the left side. So I'm subtracting 7, bringing that over. Now I'm going to switch this into logarithmic form. It's been a little while. You might want to look back at the 7.3 notes when we switched back and forth between exponential and logarithmic form. The way this worked is you take the base number, that's the 6, that is the base of your logarithm. The 42 is the argument of the logarithm, and the exponent is what gets placed on the other side of the equation. Okay, now keep in mind, the whole goal here is to solve the equation for x, okay? Now, we're close. I have a few things I need to get rid of. So we have log base 6 of 42. I want to subtract this 1 right here. So I'm going to subtract 1. Now, be careful. You can't actually subtract the 1 from the 42. I might put this logarithm in parentheses so we don't try to do that. Okay, that cannot hop in here. You can't make this log base 6 of 41. Okay, this is totally separate. And then after the 1's brought over, we would need to then divide by this 2 right here. Okay, now we've solved for x, but we need to actually get a value for x. And so this is where the change of base formula comes in. For this part right here, since that's not a common logarithm, we're going to replace that with the change of base formula. Okay, so I'm going to write a fraction. Log base 10 in the numerator, log base 10 in the denominator. The original argument stays the argument of the numerator. However, the original base becomes the argument of the logarithm in the denominator. You want to be careful when you type this into your calculator. If I were you, I would enter this in pieces. I would type log base 42, divide that by log 42, divide that by log 6. I'd hit enter, then subtract 1, hit enter, then divide by 2, hit enter. You do that, you should get an answer of 1.54. Okay, you do not check your answers to these because these were not initially logarithmic equations. We don't need to plug things back in because there are no arguments in these original equations. There's no logarithms here. Let's go back to example B and we'll finish with this one here. Okay, what has the variable in the exponent is the 3. I would say that that is already isolated. There's nothing extra. So I'm going to go ahead and switch it into logarithmic form. The base on the log would be 3. The argument would be 15, and I'm sorry, getting this all messed up here. And that should be equal to the exponent, okay? To solve for this x here, I'm going to need to subtract 1, okay? So I'm going to keep that minus 1 separate. Okay, and to get the actual value for x, I'm going to need to do the change of base formula for this part here. So I'm going to replace that with a fraction. I'm going to do log base 10 in the top and bottom. 15 is the argument in the top. 3 is the argument in the bottom. Okay, I'm going to type all that into the calculator. I get as my answer 1.46. Okay. All right, so we talked about some word problems. We talked about how to solve exponential equations by switching it into logarithmic form and then doing the change of base formula. There are problems for you to go ahead and do for homework on worksheets.